SwayamPrabha. Digital India. Educated India.
Welcome to this tutorial. Today we will solve few problems based on vapor power cycles. So let's start with the first question. An engineer has proposed that a simple ideal Rankine cycle that uses refrigerant 134A be used to produce work with heat from a low temperature thermal energy reservoir. The reboiler operates at 1.6 megapascal, the condenser at 0.4 megapascal and the turbine inlet at 80 degrees centigrade. Okay. Determine the refrigerant mass flow rate needed for this cycle to produce 750 kilowatt of power and the thermal efficiency of the cycle. So this is the sketch of the Rankine cycle. Okay. So this pump compresses this liquid from the state 1 to state 2, then heat is being added at a constant pressure in the reboiler and it heated the refrigerant from compressed to superheated state in the state 3. Then in the turbine this refrigerant gets expanded asymptotically to the state 4. So if you see the whole process on TS diagram, so the process 1 will start from the saturated liquid. So it is compressed asymptotically from the state 1 to 2. Okay. Now heat is being added in the reboiler at a constant pressure. So the state will change and it is added till it's superheated. Okay. So now from the state 2 to 3, this heat is being added and because of that temperature is increasing. Now further it is asymptotically expanded in turbine. So it will come from 3 to the state 4 and finally from the state 4 to state 1, because it loses its heat to the surrounding and comes back into the saturated liquid state. So this is the complete ideal Rankine cycle. So heat is coming in here and it will lose heat here. Okay. Now we need to find thermal efficiency and the mass flow rate of the refrigerant. So it is given that initially a condenser is working at 0.4 megapascal. So this is the pressure of state 1 and reboiler is working at 1.6 megapascal. Okay. So this is the pressure at state 3. Since pressure at state 1 is 0.4 megapascal, so enthalpy at that state will be equal to enthalpy of the fluid at this pressure. Why? Because this is saturated liquid, so there is no vapor. So from the table A12 we get H1 equal to 63.94 kilojoule per kg. Okay. Corresponding V1 will be volume at 0.4 megapascal. Okay. So this will be again 0.0007907 meter cube per kg. Okay. Now, so during this compression work work done by the pump will be equal to change in flow energy of fluid, because here if we calculate work done by the pump, it will be just change in flow energy of the refrigerant, which will be V1 times P2 minus P1. Okay. So, V1 we already calculated, so it will be 0.07907 meter cube per kg times pressure P2 minus P1. P2 is 1.6 megapascal, which is 1600 kilopascal minus 400 kilopascal. So, this gives total 0.95 kilojoule per kg. So, this much of work is being done by the pump on the refrigerant. Okay. From the energy balance on the pump, we get H2 equal to enthalpy of this state 2 will be equal to enthalpy of the saturated liquid plus work done by the pump on the refrigerant. So, this will be equal to 63.94 plus 0.95 kilojoule per kg. So, after solving it, we get H2 equal to 64.89 kilojoule per kg. Now, it is given that boiler operates at 1.6 megapascal, that is P3 equal to 1.6 megapascal. T3, the inlet temperature is also given, which is 80 degree centigrade. Okay. And so, it is a superheated state. So, from the table A13 corresponds to these conditions, we get S3 enthalpy at the state 3 equal to 305.07 kilojoule per kg. Okay. Now, further corresponds to this condition, S3 entropy will be equal to 0.9875 kilojoule per kg into Kelvin. Since condenser is operating at 0.4 megapascal, okay, so P4 is 0.4, S4 equal to S3 because it is an isentropic process. Okay. So, corresponds to this, we get H4 equal to 273.21 kilojoule per kg. Now, we can calculate heat coming in the cycle equal to S3 minus S2. Right. So, since we have already calculated S3 and H4, so after plugging these we get 240.18 kilojoule per kg. Similarly, Q out will be H4 minus H1. So, we know H4 and H1. So, after plugging it we get 209.27 kilojoule per kg, right. So, now we can calculate net work coming out equal to Q in minus Q out will be equal to 30.91 kilojoule per kg. Okay. From here we can calculate mass flow rate of refrigerant equal to power coming out of the cycle divided by the net work per kg. So, it is given that it is producing 750 kilojoule per second divided by 30.91, okay, kilojoule per kg. So, after solving it we get 24.26 kg per second. So, this is the mass flow rate of refrigerant. Now, further we need to calculate thermal efficiency. So, thermal efficiency is nothing but 1 minus Q out upon Q in. So, we have already calculated Q out and Q in. So, after plugging it here, we get 1 minus Q out, which is 209.27, and Q in, which is 240.18. Okay. So, this gives 0.129. Okay. So, now moving to the next question. Consider a steady flow Carnot cycle with water as the working fluid. The maximum and minimum temperatures in the cycle are 350 and 60 degrees centigrade. The quality of water is 0.891 at the beginning of the heat rejection process and 0.1 at the end. Show the cycle on a TS diagram relative to saturation lines and determine thermal efficiency, the pressure at the turbine inlet and the network output. So, if you see the process on a TS diagram, since initial conditions are given, it is given that during heat rejection process, initially quality is 0.891. So, heat rejection process will take place at a constant temperature in Carnot cycle, and since quality is 0.891, so that point will be somewhere here, and it is also given that at the end of this process quality is 0.1. So, this point is corresponds to 0.1 quality, because mostly water is here. Okay. So, quality is 0.891 to 0.1. Further, it will be compressed asymptotically since it is a Carnot cycle. So, it will look like this, the whole process will be like this. So, 1, 2, 3 and 4. So, these 3 and 4 are corresponds to 0.891 and 0.1 quality. Okay. It is also given that minimum and maximum temperature of the cycles are 350 and 60. So, minimum temperature will be corresponds to this, which is 60 degree centigrade, and maximum will be corresponds to this, which is 350, right. So, heat will be rejected here and heat is coming in here. Okay. Now, it is asked to calculate thermal efficiency. So, what is thermal efficiency? Thermal efficiency of the Carnot cycle is 1 minus TL upon TH. Okay. So, 1 minus 60 plus 273 Kelvin divided by 350 plus 273 Kelvin. Okay. So, the thermal efficiency will be 46.5%. Now, in the second part, the pressure at the turbine inlet. Okay. So, we have to calculate P2 value. Okay. So, S2 entropy at this state will be equal to entropy at the state 3, because it is an asymptotic process, asymptotic expansion. S3 equal to entropy of the fluid plus quality at this state 3 and SFG. So, at this temperature from the saturated water table we get SF equal to 0.8313, quality is given 0.891 at the state 3, 0.891 into 7.0769. Okay. So, after solving it we get 7.1368, okay, kilojoule per kg Kelvin. Since T2 equal to 350 degree centigrade, okay, and S2 will be equal to 7.1368, because it will be equal to S3, right. So, kilojoule per kg into Kelvin. Now, we know state 3 informations T2 and S2. So, corresponding to this condition we can calculate P2, okay, which is 1.4 mega Pascal, and this can be taken from the table A6 correspond to this condition. In the next part of this question we have to calculate net work, okay. So, the net work will be equal to area on the TS, area enclosed on the TS curve, okay. So, for that we need to know entropy of the state 4, which will be equal to entropy of the fluid plus quality of the state 4 times SFG, okay. So, SF is 0.8313, entropy we know which is 0.1 and 0.70769. Now, after solving it we get 1.539 kilojoule per kg to Kelvin. Thus, W net will be equal to area, and this area will be equal to TH minus TL times S3 minus S4. So, we have to do it here. So, after plugging these values TH, TL, S3 and S4, S4 we have already calculated, okay. So, after plugging we get W net equal to 1623 kilojoule per kg, okay. So, now moving to the next question. A space is kept at minus 23 degree centigrade by a vapor compression refrigeration system in an ambient at 25 degrees centigrade. The space gains heat steadily at a rate of 3500 kilojoule per hour, and the rate of heat rejection in the condenser is 6000 kilojoule per hour. Determine the power input kilowatt, the COP of the cycle, and the second law efficiency. Okay. So, if we see the process, so it takes heat from the space which is at minus 23 degree centigrade, okay, and rejects it at 25 degree centigrade, and it is asked to calculate power input, right. So, we have to calculate power input, COP of the cycle, and second law efficiency of the system. Now, the power input would be equal to Q dot H minus Q dot L. So, it is given in the question Q dot H is 6000 minus Q dot L is 3500 kilojoule per hour. Okay. So, we get 2500 kilojoule per hour, but we need to calculate in kilowatt. So, we have to change it further, 2500 kilojoule per hour, and since 1 kilowatt is equal to 3600 kilojoule per hour. Okay, so after solving it we get 0.6944 kilowatt. So this much of power going into the cycle. Next we have to calculate COP of refrigerator. COP of refrigerator is nothing but QL dot upon power going into the cycle. So Q dot L is nothing but 3500 upon this much kilowatt, and power input is equal to 0.6944 kilowatt. So COP of R will be equal to 1.4 after solving that. Now COP of the Carnot cycle. Now if this cycle operates on Carnot principle, okay, then the COP will be equal to TL upon TH minus TL. Okay. So TL is given to 50 is minus 23 degree centigrade, and TH is 25 degree centigrade, which is 298 Kelvin. So after solving it we get 5.208. So second law efficiency equal to eta equal to COP of actual refrigerator to the COP of refrigerator when it follows Carnot cycle. Okay. So now we know COP of R and COP of Carnot cycles. So after plugging value here 1.4 upon 5.208, we get 0.2688, which means 26.9%. So this is the second law of efficiency of the refrigerator. So we will stop here. We will meet you in the next tutorial. Thank you.